In this presentation, what we are going to do is we're going to look at the scalar triple product. Okay, so first off, what I have here is I have the, oops, shouldn't have done that. I have the cross product of, I'll just write it again, I'll have the cross product of, there we go, of V and W in brackets. Okay, so that's the cross product, and the resultant of a cross product operation is another vector. Okay, and then I have the dot product of U times the resultant of that. Now, just as a remark, ordering here is very important. What goes where? Okay, so V, it's not necessarily equal to some other arrangement. For example, it's actually not equal to U times, let's just sort of switch the order of V and W. Okay, so it's actually not the equal to it. It's actually the negative of it. And we'll sort of see why shortly. So I'll just actually write that in. Actually, it is the negative. Now, your resultant value overall here is going to be a single value. Okay. Now, so, this works on the basis of three-dimensional vectors. So I'm going to write here U as, I'm going to write it here as ABC in that sort of format there. V is, let's say, D, E, N, F, and W, let's say, is G, H, and I. Okay, now that's sort of column vector notation for vectors. If you're not used to that, essentially it's just equivalent to this. So I'll just rewrite U in just one of the other formats there. AI plus BJ plus CK. Okay, and another format again using X, Y, and Z. I'll just write V here. That's equal to DX plus EY plus FZ. There's multiple different types of format, okay? Actually, and what I will do there is I will use the second one. Well, not that it really matters, okay? So, as long as you're sort of pretty consistent, have one and just sort of stick with it. Okay. So, anyway, the ordering here is very important. So, the scalar triple product, U dot V cross product W, okay? And they're all vectors, can be written as, so first off we have A first, and this is going to be the top column of this matrix. We're going to create a matrix, okay, and actually, to cut a long story short, we're going to get simply the determinant of it. Essentially, this is altogether just a determinant of a 3x3 matrix. That's to cut the make it a long story short. Okay, so there we have it there. So what I'm going to do here is I'm going to go to this next page here, and what I'm going to do here is we're going to sort of try an example here. So I'm going to put this in here as that we're going to let U equal, let's say, just clear it off here. Let's say that we'll let this 1, 2, and 6. We let V equals 4, 3, and 0. We let this equal 1, 2, and 0. Okay, and that is our matrix. So let's write it out here. So the top row is U. Okay, so that's going to be 1, 2, and 6. Okay, 4, 3, 0, 1, 2, 0. Okay, so essentially now I've sort of partially picked it out such that we got a column that actually has a lot of zeros. So essentially our triple scalar product is the determinant of this matrix. It's a 3x3 matrix. What we're going to do here again is pick out a row or column. Okay. Now, and then what we're going to do is simply get the determinant of that. Just as a remark, this is in the plus position of the sine array, this is in the minus position, this is in the plus position. If you're not familiar with sine arrays, you should really check out how to get the determinant of a matrix. So what we're going to do here is 6 times its minor matrix. Well, actually, the minor submatrix is the proper term there. Get the determinant of that. 4, 3, 2, and 1. Then minus 0, but you don't really have to go anywhere with that because it's going to cancel out to 0. Okay, so essentially you don't really need to calculate the rest of it there. It just turns out to 0. Okay, So what we're left with here is 6 times the determinant of that. That is 6 times minus 2. 4 minus 6. Okay, so the answer is minus 12. The scalar triple product is minus 12. Okay. Now, there's a sort of geometric interpretation of that, but I'm going to sort of leave that for another one. It's how to get the volume of a parallelepiped. But for the time being, what I'm interested in here is how to just calculate it in a nice, simple, orderly fashion. So that's it there, scalar triple product for matrices.